for streaming data that is used for Wi-Fi. The algorithm is RC4. So in order to implement RC4 algorithm, not all of you, those who wants to implement, needs to know a little bit of Python, the primitive techniques like this. Percent sign. Why that is needed is because that is good for hash code. Okay? So modulo, for example. 17 modulo 3 is, as we looked at last time, what is it? Yeah, 2, 3 modulo 17. This is a 3, right? So can we make it in Python? Of course we can, right? So how can we do? The way that you could do is to bring command line. So I'm going to bring the command line here. Well, I'm going to make it smaller. I know some of you do not like small window, but if it is not small, I cannot make them here together. Okay, thank you. Yeah, I cannot see my mouse. This. Oh. Yeah. Okay. Before I really forget, I need to explain to you. For those who do not know how to find the research topic or how to elaborate, I know many of you not clear what to do, your project, although you submitted. Still okay, you can modify the topic. This is the right phase that you can modify, tweak, or change the topic, but before too late. Okay, don't change it 2 weeks before the deadline. Okay, we still have about a month. Okay, about a month. Still okay. I don't see anybody doing the project more than or longer than a month. So this is the right time. So how can you find it? Here is what I do usually. If you want to do, then you can go to
White House and Trump.
Oh, you want to ask the topic to Trump? Go to our Mercy website. You can start from Mercy website, and then there is a tab, Academics, and Digital Library. Library Home. And then there is a database by name. Do not type yet any, but a database by name. And then there's the alphabetical order. The article that I ask you to use, and also I'm using that a lot, in this category A, where there is ACM digital libraries. How many of you frequently access these ACM digital libraries? Thank you, Mark. Let's talk. Almost all computer science and cybersecurity computer information systems scientists come and read articles from these digital libraries. If anyone in that disciplines still make significant research output without this access, then that is a lie. That person is a liar. There are so many liars. Okay? What I mean by that is, this is very, very important to digital libraries. If you never come here, then this is the right time. If you click that at home, then it will ask you to enter your credentials. You can use your Mercy Connect credentials, login name and password. At school, you do not, this guy does not ask you, because we have site license. And then there is a text box that you can enter for, I'm going to pick two students. Eureka. What is the keyword that you are interested in security and wireless? Of course, wireless. Let's put
Hacking.
okay, wireless hacking. I don't see it. So if I have a typo, please let me know.
You don't see it either. It's too far away.
Edmond, I think you need to go home.
I really need to go home. I'm just doing this one that I really need to.
Wireless hacking. Oh, typo? Oh, okay. So there are how many articles? Per page there are 20. How many articles? At least 20 times 10, then 220 articles talking about not 100% purely solely about wireless hacking, but each article is talking about a little bit related to wireless hacking. Okay, so once you get in, then you can pick, for example, review Wi-Fi secrets of wireless hacking. Oh, that's good, right? Although it is written in 2004, if you are interested in this, then there's an HTML version and PDF version, so you can download one of those. And also, there is a good, if it is a good article, then there's a citation count. If there is a citation count 0, then no one referenced this. Although it has been searched 1,700 times. Okay, last 6 weeks, 15 times.
Only in our library or in this website? Like
In this,
Oh.
yeah, in this website.
All right.
Not from
Mercy, yeah.
Mercy.
I was like, who's-
Mercy, I think
We didn't have
I may be only one
1,000 some
using.
graduates.
Right. And improving a live migration process of large enterprise applications. So you can use one of those. For example, wireless insecurity. If I click this PDF, and then you can see this is not really technical paper, but this is a good article that you can use, okay? And come back here to the previous tab. Some others. Here, wireless hotspots. PatriNet has been used a lot for identification. Okay, this is something that you can start with. So Eureka did. I'm going to ask, for example, Martin. Marvin.
Yeah.
Your name is Martin or Marvin?
Martin.
Martins. Okay, Martins.
Yes.
Give me 2 keywords. of your interest, and that may be related to this course, so that you can find some relevant articles.
Okay. Streaming data?
Streaming data, that's good. Streaming. Security is really need. So bleach. Streaming data bleach. Gene Samuels, British computers. Theory of data stream computing. Research issues in mining multiple data streams. Sketch. Let's see. Attack. Oh, here, live streaming attacks. Sounds good, right? So you can click PDF. Oh, Dr. Chen wrote this. No. Yeah, Beijing Jiaotong University. I think he's from there.
Are you sure there is a guy on there who has a similar name?
I know. This is not his.
This one is
Yeah. His first name is this. His first name is not this. But anyway, you can read some of this.
I remember looking one up and being like, is that like a Chen? And then it wasn't, but it was really similar.
You know, there are millions the same last name,
Yeah.
Chen. Chen is one of I think top 5
Yeah, but I think it was
popular
something like
last name.
Zuzong, too.
Yeah. Chen is very, very popular. Chen,
Chen, yeah.
yeah, in Chinese.
Chinese, yeah.
Yeah. So you can find the articles. Without reading articles, doing research is almost impossible. Number one. Number two, almost valueless. It is something like a building built upon sand, dust. I want you to build your building on top of rock. So rock, solid foundation. Right, Eureka? Okay. So this is just minor comments before we close that. All right. So let's try this. This modular. Oh. Like this. 17 percent modular, and 3 in Python, then it returns 2. Okay, so we need to call Python. So I'm going to call okay. Then I can say 17 yeah. Okay. Or you can do right? As we expected. And what? You don't need
I wanted to help
to.
you.
I know, I appreciate, but
I didn't help.
I wanted to focus on
I wanted to help you.
course material. Okay. We did this last time, exclusive OR, right? So can you do that exclusive OR here, somewhere, right? That's what I want you to do. So in order to practice it, what I'm going to do here, where are we? Oh, here. I do not want to do this. And for example, when I ask you to apply RC4 algorithm to make a cipher text of Mercy College, then Mercy needs to be first converted to binary code. So how can you make a binary code? One thing that you could do is in Python, for example, if it is M, then old means ORD is an ordinary number. Ordinary number counted from whatever the ASCII code. Okay, so small m is 109. For example, old small a is 97. Ordinary number uppercase A returns 65. Things like that, right? So that is ASCII.
Can you do it directly in Python? Like
This is Python.
I know, but can we do it directly? Like find the binary code for M. Don't go through each one.
Like it's a function? Like,
What do you mean?
Like when we type, for example, M, show us the binary code for M.
Oh, binary. Yeah, that's what we are going to do right now. So in order to make a binary code, then you need to use another function called format. Format takes the binary code of, for example, A. This format function can convert that, for example, this ordinary number, odd A, small a, returns 97, which is 97th in that ASCII number. So we want to change it to B for binary. I want to reformat this 97 in binary code. So when I enter this, then it returns binary code. That is a binary code of small m.
Small a.
A small a, for example.
where's the small b for?
If there's a small b, then there is a one higher than that, right? Okay, so can you explain? What is a b? What is a binary code of small b? By knowing binary code of small a.
Format
So what is the binary code of small? Huh?
I don't know the binary code.
You should know because you know a. B is one above that, right?
Yeah.
So if you add one more, then what is it? 110010?
Yeah, 10.
That is it, right?
Yeah, and then 1
And C means?
1 1.
Thank you. If you want to make this hexacode, this is hexacode.
But it's the same thing, right? Hexacode that is
C is 97, 98, 99, right? 99 is the lowercase c. 99 in decimal is 63 in hex.
I thought hexadecimal works with ASCII. Like it's the same.
No. Hex is base 16.
Yeah, I know.
So, for example, If you know, then why you say that? For example, 12. 9 is 9, right? And 10 is what?
Hey, BC.
Thank you. A.
Yeah. Oh, yeah.
So 63 means up to F and then 1, 2, 3, 4. Okay. So if you want to convert to, for example, Mercy College, then you can say text equal Mercy College, right? So text is Mercy College. How can you convert to Mercy College into binary? Using format. For X in text, and then format old X and that. Then there is a Mercy College. This is a small uppercase M, M-E-R-C-Y, this is space. C-O-L-L-E-G-E.
Can you zoom it out for?
No, man, it's Samsung.
Yeah. That's cool.
No, there is explosive. So if we send the text to you, then explode.
It's not. It's not the note. The note explodes. It is from there.
I know.
So,
I'll fix it. If you want to put them in one binary code, how should we do? That is this. Where is my mouse?
Why do we have to convert it to
Probably
binary
not.
to put it into ciphertext?
This. For example, I want to this right now. What we did here. Each character returns binary code. Can we have one binary string? So that is the code. You need to join whatever you have with the initially empty string. Okay? So how can you make it? Similar to that. Then you need to do dot. There's a join function, and then format the one that we did, or ordinary X, and I want to change it to binary. Format that, and for X in text. Everything should be here, right? And enter. And that is whole binary Mercy space college in one binary code. So if you see here 1001101, that is the 1001101, followed by 11100, whatever that. This one is that one, yeah.
In order to put it into ciphertext, we need to put it in binary.
That's what yeah. So this algorithm needs, that's a good question. You have a great insight. Why we need to learn this? The RC4 algorithm is going to do with binary code. Why? The one that we learned, the last class, 2 weeks ago. Which operation, because of which operation we need to change it to binary code. Exclusive OR. That's right. You're smart. You can go home. You don't need this. But actually, exclusive OR can be done in Python, but why we need to switch it to binary code is because that's clear for us to understand, right? We don't need to. We simply do exclusive OR, then binary code, Python can do it. But we do not know clearly how it operates. Okay. But anyway, that is that. Next slide. Now we want to work on exclusive OR. Where is my mouse? Oh, right up there. Okay. So, so this is exclusive OR operator in Python is caret, right? This is a caret, so-called caret. So, if you want to exclusive OR 17 and 3, then 17 caret 3. Then it returns 18. But we do not know how. Is it really working that way? So that we can convert to 17 here using this. We already know this, right? 17 into binary code and 3 in binary code. But still, it's not really easy to do exclusive OR. So there is another trick that I made just this afternoon. So that earlier version of this course material does not have that, but I revised it. So you can find out the recent one. The exact same one here, right? But I made here up front. Here's a little track. Format 17, that is okay. I didn't do anything. But only because 11, if I don't do that, then 11 appears up front so that I cannot operate that operation on this screen. I want to shift this to the end of that margin so that, like this, so that I can compute. I can compute clearly. What it does is that this format is a function that can you can render the text. This is a text, right? Because within quote, right? That's a text. But if we have curly brace, like here, curly brace, followed by dot and format, then this, if we have any number here, starting from 0, 0 can be omitted if we have only one text to render, right? But if you have a multiple text, to be rendered in different formats, then number 0 in this format, number 1 another format, number 2 another format, number 3 another format. Then you need to have that numbering system. Here we do not need. But anyway, if we say number 0, then anyway there is only one case. No harm. Still okay. So that is what is that, right? This is index of the text. So first the text needs to be in this format. Colon. Colon. After this colon, then we can specify in this case one more time. This is a little funny, right? I want to make it binary code. Binary code. So last B means binary code. And then there is a greater than sign and 5. Greater than sign and 5 means I want to push the binary code 5 spaces. So that is right shift operator. I want to shift the character to right. So what it does is that if I don't have this, then it should appear here from the first character, right? Like this. But because I shifted 5 times, so 1, 2, 3, 4, and 5. Why that is 5 times? Because I know that is 1, 2, and 3, and 4, and 5, so that I can line up. Just for my explanation. If I have this, then I can simply exclusive OR. What is a return? And also, if I can put here zeros, oh, that is so nice, right? I will do it. I'll show you how we can make a 0 here. So if I have 0, 0, 0, 1, 1, 0, 0, 0, 1, 1, if I don't have that specific shift and so-called character padding, that's a character padding, right? I want to pad the character. If I don't do it, then although I put zeros, 0 is even odd, right? But I explicitly, I can do padding. Then I can simply manually and visually understand what it returns is, according to that exclusive OR, 0 and 1, because they are not the same. So it returns 1, and 0 and 0, it returns 0, and 0 and 0 returns 0. And then now here, 1 and 0, so it returns 1, and finally 1 and 1, therefore it returns 0. This is the result. That is what we have here. See, in another way, I make 17, the format 17 and B, I assign the two variable A and variable B, and then I apply exclusive OR, exclusive OR, which is 18, but I want to make it 2 means this is a binary, right? Base 2. I want to convert that to binary. So these two binary code are exclusive ORed and assigned to variable B, and finally that variable B format is again converted to binary here, as we did here. This exact same one, right? Therefore, it returns 1, 0, 0, 1, 0. Okay. So, together with you, what I want to do, all right? Okay. Here, like we did here, it's not really clearly seen. Okay, it's perfect. So what I want to do here is 0, colon, and greater than sign. First of all, we can do simply B, colon, and B. This is text, but I want to format 3, B, and it returns a 1, 1, which I do not like. So what I want to do is I want to shift it to 5. I want to shift it to 5. So it shift 5. And if you want to pad, if we want to pad the zeros, I'm not sure, probably should be here. I want to pad 5. Okay, good. So instead of a blank, I want to pad 0. Whatever the empty space, I want to put that 0. So 0, 0, 0, and 1, 1. Okay. It's a little bit of tricky here in Python. But Python is a good language. You cannot do that in Java. If you want to do it in Java, then it's not impossible, but I've never tried. Don't waste your time, but play in Python. All together, if you want to do all together, then this is the thing that you need to do, okay? For example, is okay, so colon B, okay, and then format int, format 17. I want to make it the binary, which is int number and binary number 2, and then I want to make it exclusive OR. So a little different. That's okay. So int, format, and 3 binary, and comma 2. So what happens here is this we have a format, open, 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 close with that, and this is closed of that integer. So one more format should be closed, probably at the end. So I have int format. This is close over that. This is close over that int. The last close parenthesis is close for that format. Okay. So so it returns this 10010, the same as what we have here, multiple steps, but here is one step, one statement. Okay, question? No question. Good. Now we need to discuss about. Is it already 8? No. Oh. Portable and mobile. Portable station moves from a point to point, but is only used at a fixed point. Mobile stations access land during. It's not really a big difference, right? So here is what we want to do. In the mobile services, we have two locations: station service and distribution system services. Station service means your laptop. Okay, when your laptop tries to access access points, then let's say that is at the distribution system services. Your laptop needs to associate or reassociate, disassociation, and so on and so forth. This is what we discussed, I think, several weeks ago. And distribution system services is doing that. Only here in this case, this guy has your laptop can do association, but your laptop cannot do deassociation. Only deassociation can be done at the other side. Association. Okay, so Wi-Fi currently have WAP2, is it WPA or WA? WPA, right? WPA2, and more advanced encryption algorithms used, but they are all stemmed from WEP, and WEP algorithm is released. So what we want to do here in this class, we want to use that algorithm, which is called RC4, right? Here, RC4. R is a last name from that guy, and C4 cipher. And there's different versions: RC4, RC5. RC5, I think that is the algorithm used for WPA1. Okay. So before you send the message, therefore encryption is needed. What we need to do is authentication. Your laptop needs to authenticate the server, which is AP, access points, so that access point and your laptop can communicate. In order to that, your laptop needs to associate, right? This is an association model. There are two kinds: passive scanning or active scanning. By that we mean here we have here laptop. Where's my Okay. All right. This is my laptop. I have 2 access points. If I want to move, or if I am in between, then in many situations, right? I want to move from one access point to another access points, right? Or you maybe try to access at that joint area. In any case, this is a particular situation. There, you are simply response to the beacon signal from access points. So access points usually send out a beacon frame. Beacon frame is nothing but that is also a packet, right? So if you see the Wi-Fi, Wireshark, then you can identify the beacon frame initially when you turn on your laptop. But without programming to collect beacon frame, I think it's initially when you first access points, the hundreds of packets are sharing, so very easily miss that out very quickly. But anyway, beacon frame comes in your system, then your system replies to that. So your system wants to associate. So associate request. So request is sent to the access points. Then access points response to that access request. So that is passive scanning. On the other hand, we have active scanning, which is if you have 2 access points, then they need to know each other. So probe request frame broadcast from H1, one of the access points, and probe response frame from another access points. So they need to probing before association. So in this case, this laptop can be solved by negotiation between those 2 access points, which is the access points are actively scan your laptop and provide the services actively. Okay, there's 2 kinds of association. Once it is associated, then we can authenticate. Okay, so authentication produced in this way. Host request authentication from AP, and AP send 128-bit nonce. Okay, what is nonce? (128-bit nonce). So access points send out a nonce. Then your laptop needs to do something with that nonce, and then send it back to access points. So access point verifies, oh, this guy I want to serve. The nonce is, somebody tried to say?
One-time use.
Yeah, one-time use, right? Only one-time use.
Number ones.
The number generated once. So nonce, so host encrypt nonce. So host means your laptop. Your laptop, nonce is provided by access points. So your laptop receives nonce and then encrypt it and send it back to, and also access points send symmetric key as well. Okay, not only nonce but symmetric key. So symmetric key and nonce together, therefore your laptop encrypt. Your laptop can easily encrypt nonce because nonce is given. Nonce is nothing but a code, the number. Okay, some word. String used once or number used once. And using the shared symmetric key. So you have the key and you have the nonce, simply encrypt it and send it back to access points. Then access points decrypt it, decrypt that nonce, and then nonce is the same nonce that this access points initially distributed. Then this access points, hey, yeah, I can take care of you. So that authenticates. And once authenticated, host can send the association request, no key distribution mechanisms, and in this way, authentication and association is done. Okay. Once authentication and association is done, authenticate so that trust and associate. Now we are ready to communicate. After that, then you need to send out the message. When you send out the message, that is the point that we need to encrypt. So encryption comes after this. In this slide, we want to see nonce. Nonce can be generated by many ways, but simple ways that we can emulate here is to use a random number generator. Random number generator. Okay? So we can generate the random number. So random is a module, and then you can say rand integer from 0 and 9, then it returns you the random number. But right now, I'm not sure random module is imported. If it's not imported, then we have to import. Okay, import random. Random is given, so you do not have to install it. Once you have that, then random and then there's a 7 right now, right? Can you make this, for example, for, I want to make for I in range 10. And validate the syntax, right? Because it's just a random number. So if you want to make a string, so make a string, what we need to do is to similarly that we do, because we want to make a long string of that. So using join, and I want to put in the list. So that's list. This random open and close. This is random number, and this for that, and okay. And then simply close to join, then it returns that random number. So I have 10 random numbers generated, right? If we want to, for example, 128 random numbers, I want to generate 128 random numbers. That is my nonce. That's possible, right? If I want to do it right now, then it's different. Every time when I do this, it's different. So once used, then never have that nonce. Many ways that you can do, or you can do time, or UU universally unique ID generator. It's UUID. That is another possible. For example, UUID dot UUID 4 and hex, then returns. It's not, so we need to import UUID, and then this, that is UUID. Universally unified ID according to the version 4. So UUID function version 4. I want to convert it to hexacode. So what is the size of this? I think 16 bytes, right? This is 1 byte, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. 16 bytes long. So 16 bytes long is the universally unique ones. Okay, there's a nonce. Okay, so recap. Authentication key distributed out of bound, out of band, access points generated randomly, generated challenge, station encrypted challenge using pre-shared secret, and that is possible. Okay, that is authentication. Okay, now we want to see RC4 stream cipher. Host 10 AP means your laptop and access point share 40-bit symmetric key. So share 40-bit. Symmetric key, and host append 24-bit initialization vector, which is ID. So we combine them together. So total 64 bits is from the key side. Okay. 40-bit, that is the key, 24 bits, simply initialization vector. So 64-bit key is used for WEP encryption. If you want to increase this 128, then you need to increase the others. So if you have the key with the initialization vector and the message that you have, and apply exclusive OR operation, then this is a cipher text, and this cipher text now is shipped to. So more clearly, it is written in this way. RC4 is a stream cipher, generates pseudo-random key stream from the key initialization vector here, and exclusive OR with the key, and whole thing is the key
So that is the encryption key here. Okay, with this. So that is the key. So here, this is the operation going on here. And using the key, given plain text comes, right? This is streaming data. So comes continually, right? And if this is a 64-bit, for example, then every 64-bit is compared with this and exclusive OR with this. And the outcome of this exclusive OR operation is the ciphertext that is sent out. So at the receiver side, if it is arrived, then using the same key, using the same operation, therefore we have the original plain text. That's what it is. So mobile station shares the key with the access points. So your laptop and access points, they share the key. When did they share? Remember that earlier when we access points first send out nonce to your laptop with the symmetric key. And then with that symmetric key, your laptop encrypt it and send it back to the access points. So if access points receive it, that means your laptop is real. Therefore, from that time, you can solve. So that key is used. So that is a shared key. Okay? And then transmit message. If you have a message, okay, if you have a message M, then compute checksum of P. So checksum needs to be attached to this message in order to correct the message if there is any errors. So checksum key. There is also 64 bits. And using RC4, it generates a key. So this is the key. This whole thing is the key. And this message and checksum all together is a message. This is a message. This is the key. And the exclusive OR operation. So from next slide, what we want to do is that once you have a key, small key, once you have initialization vector, then apply it to RC4 algorithm. So RC4 algorithm generates the key. Here is what we want to do. Encryption algorithm is a RC4. Key length is 40. And initialization vector is 24 bits. Okay, so it generates the key, which is this, and this is a message. We want to do exclusive OR. So we have a message, and according to the message, we can attach the correction key, correction. And then generate key stream and exclusive OR and send it. And therefore we have a ciphertext. And ciphertext. So this is the recap that I explained so far.
actually, the algorithm that we looked at was for 64 bits, but we can increase that into 128 bits. There is still RC4 and all others, the same as before. This is the algorithm, okay? So let's try to do this algorithm. Cipher internal state consists of a 256 bytes array S, which contains a permutation of 0 to 255. Total number of possible states is 256 factorial, which is 2 to the power 1700, which is too big. So let's try to use two index, I and j. Initially, start with 0, so I equals 0, j equals 0. So we have a loop from here, there. And I and j keep changing. Okay. And S is given 256 byte array, which is S. So Si and Sj swaps. Output is Si plus Sj at the end. That is the end of the loop. So that is implemented in this way. This is also for initialization. That is algorithm. I want you to take a look at that. Before we do everything, this is a real example, but I wanted to understand those two algorithms. I mean, it's a simple algorithm, but I wanted to follow what it means by looking at that pseudocode. For I equals 0 to 255, Si equals I means S will be just numbers, right? S will have 0, 1, 2, 3, and then all the way to 255. So S is generated. And J initially equals 0, and then for I equals 0 to 255, we want to do this. So J, so we want to swap this given generated initialization vector. We keep swapping, but I is linearly increased from 0 to 255, but J is generated. Okay, this is J can be generated from J plus S over I. So we need to pick second value from this vector. And third one is, this is a key, this is I, small I. I mod L what is L? Something missing. And everything together from here there, and then we apply mod 256. Then we have I and J here. These two index, they are indexed here, right, in this vector. So pick up the value and they are swapped.
we keep doing that. 256. If you want to do it manually, then it's almost impossible, right? So for our manual example, we want to make it simple. Okay, use 8-bit only. So key is, let's assume that key is right now 1236, and plain text is 1222. Step 1 is initialize S. So S is, we simply enter, right? S is simply enter from 0, 1, 2, 3, 4, 5, 6, 7, 8. So we simply enter it. This is S. And T, because we have 4 bits, let's say this 4 bits is another attachment, right? So what it does is that this key is repeated, 1, 2, 3, 6, and 1, 2, 3, 6. If you want to increase this vector to 16 bits, for example, 8, 9, 10, 11, 12, 13, 14, 15, and 16, if this is the size of that vector, then we need to repeat this 1, 2, 3, 6, and 1, 2, 3, 6, and another 1, 2, 3, and 6. But anyway, we can generate S and T. Okay. Initially. Any problem? No problem. Right? So simply generate it. Okay. And this is algorithm. That algorithm is from this part. Right? We generate S, and this is the part. Okay, here. Okay. Oh, not this. Yeah. This you want? Okay. So that we have S and T. This is simply generated. We enter from 0, 0, 1, 2, 3. So sequence number, depending upon the size of the key. Right now, we simplify it 8-bit only. Our key is 4 bits, so to match it, we repeat. So apply the second portion of that algorithm, okay, which is here. Let's say j equals 0, and then we have a for loop. For I equals 0 to 7, because we have only 8 bits. Okay. And then j, so for I, we need to compute j, and finally we want to swap. Okay, that was the algorithm that we looked at. This is a simplification. So, for I equals 0, this is the first step. For I equals 0, we need to compute j according to this algorithm. J is, open parenthesis, j plus si. So j is 0 initially, right? J is 0. So that is 0 here. And this comes from S of I, but I is now 0, so S of 0. S of 0 is here, 0. So that is 0. And then the last component here, last term is t of I. So this is t of I, but I is currently 0, so t of 0. So t of 0 here is 1. So we bring that 1 here. And modular, because the size of the bit here is 8, so we modular 8. Then 1 modular 8 is 1. So j is 1 and I is still 0. Now we want to swap here. Swap S of, what we need to do is swap S of I means 0 and swap S of 1. Right? So S of 0 and S of 1. Which means, come back here, the vector x, s. So 0 and 1, these two needs to be swapped. So we have here. All the rest remains the same. This is done for only one iteration from this for loop. See of this for loop? It starts from 0. So now we need to think of the 2. I equals 1. Okay? When I equals 1, then we also compute j. J equals j plus s of I and t of I. So j equals j, which is the previous j here is 1. So that is j. This is s of 1. And this is t of 1. S of 1, we need to now, S is changed. So we need to come back here. What is S of 1? There is a 0. So that is 0. T sub 1, T never changes. Still here. T sub 1 here. So number 2. So number 2 comes here. So altogether 3. So 3 modulo 8 is a 3. So we have to swap. One and S of j, which is a 3. So what is S? The S that we want to work on, there's a current S, which is this. So S of 1, this guy, and 2, 3, this guy, they need to be swapped. So 0, 3, 2, 0. So 0, no, 1, 3, 2, 0. 1, 3, 2, 0. It remains the same. That's the second iteration. And then third, which is I equals 2. Okay? And then j can be computed in the same way. J equals, what is the current j? Current j is 3. So we need to plug 3 here. Plus S of I, what is S of I? Which is S of 2 and T sub 2 needs to be plugged, right? So S of 2, come back here, S 0, 1, 2, there is 2, so number 2 here. Plus T sub 2 all the way up here 0, 1, 2. So it is 3. And mod 8. What is it? 3 plus 2 plus 3 is number 8, right? So 8 mod 8 is 0. That is the way that we have 0. Okay? After this, we need to swap. So swap S of 2 and S of 0. So what is the S that we want to work on? So recent 1, current 1. S of 2 is 0, 1, 2. This guy. And S of 0 is that guy. Those two guys needs to be swapped. So 2 appears first, and 3 and 1 comes here. They are swapped, and all the rest the same. This is the third iteration. And fourth and fifth, sixth, all the way to the 8 times. We have to do 8 times. So now your turn.
One question.
So I want you to do this, the case of I equals 3. So J will be 6. So to see if your calculation returns J equals to 6. And then swap. And further and further and further. Question.
So, how do we crack it then?
Once you know this, then it's simply, right? So after we know all, then we can think of that. So we do this all up to 7. Then we have S here. S finally will be, what happens here is that if we have 256 bit, then those all numbers are swapped, and finally you have all different kinds of numbers, all in different order, like this. What is the vector that we started with? The vector that we started with was 0, 1, 2, 3, 4, 5, 6, 7, right? At this end, these are all swapped. And then we have second phase. Second step is, the third step, according to that. Then we have another while loop. After this while loop is a lot simpler than earlier. If we do that all, then we have the first key is 5. 5. Something about the 5 is exclusive over 1. And if we do another while loop, whatever the number that is exclusive or with the number 2, and another number that is exclusive or with this 2, and another one that works with that. The whole thing with the exclusive OR, and then we have that number here, whatever that number, binary number, and that binary number like this. That binary number is converted to the real text, in this case number 4, or some character. So that the scrambled character is sent out. So at the receiver side, that scrambled number, scrambled character needs to be converted to the binary code, and then generates this cipher, the key, string key, as we did, and then apply the exclusive OR operation. Then you will have the original text. This is very straightforward, so that programming is very, very straightforward. A couple of years ago I made it. It's here. in Python, but if you want to do it, you can do it for your project. But right now you have to practice by manual. Doing so by manual, then you can clearly see all the procedures. Therefore, programming will become much simpler.
Do it on paper?
Yeah, do it this on paper, but this is time for break. So let's take 15-minute break. Come back by 8:10, and then we can do this. Continue. Okay?
Let's do this on paper so we understand how it works.
You should. You should understand.
You did? You did it on paper?
Oh yes, I've done this. And then,
Thing is,
and then what I did is not the 8-bit only. I did 128 bits. I mean 256 bits. No, not on the program.
It takes so long.
The implementation, you can play with the 8 bits and make sure that it works. If it works, then you can simply change the number in your coding. Simple number, then it's okay. Okay. Here's what I'm asking you. Anybody has done this?
Huh?
This? No, not yet, right? So I want you to do this, another homework assignment, okay? So completion of this. So simple homework assignments. So let's assume this is the finally that we have. Then next step is having this. Look at this, the algorithm. I want you to read the algorithm carefully and see how's it going on. This is the key. Finally. So what is the size of a key that you can generate? In general, there's no limit, right? This for loop works forever. As far as it's true, it goes forever. So this algorithm generates any size of the key, but it generates one bit of key at a time. Actually, not one bit, but one number, one character. Okay? So let's take a look at. We need to play with the two indices, I and j, like we did in the previous algorithm. So once you have s, here. Once you have s, in the previous example, then come back here, calculate I from given I and j. Initially, I and j both start from 0. So 0 plus 1 is 1. Mod 8, then that is still 1, right? That is this. And then the index j is computed similarly. So initially j is 0. 0 plus s over I. What is I at this point? I is 1. So come back here, s over I is, okay, here. S over I is 3, number 3. Okay, so this is number 3.
Is that an I or a 1?
This is I. This is I, but I is this I. But this I is currently here. So S of 1, which is 3. So 0 plus 3 mod 3 is 3, right? That should be swapped. Once you have I and J, then we need to do swap based upon those two indices. So I equals 1 and J equals 3. So we need to swap I and J here, right? S1 is 3 and S3 is 4, up here 4. So those two numbers are swapped. So at the first swap is we have 2, 4. This 4 and 3 are swapped. So 2, 4, 7, 4, 6, 0, 1, 5. That is given. That is obtained. And now we need to do S of I plus S of J, add them together and modular by 8. So S of I, what is I currently? 1. J still 3. So SI, so take 4 and 3, add them, which is a 7, which is a 7 here. I'm sorry. So this is a 7. 7 modulo 8, then that is a 7. Finally, key comes from S of 7. So key that we obtained is S of 7. This is that. So 5 is obtained. Okay, so 5 is nothing but 1001 in binary code. And that is the first key, so that is matched, that is used to for encryption for the first letter of the message, so which is number 1. So we make exclusive OR. Number 1 means 001. So we make exclusive OR. Therefore, we have 100. So 100 is now finally converted to the hexacode, which is 4. Okay. So the message that I want to send is number 1, but cipher text is number 4. And we need to do that, the rest. Okay? So I wanted to complete this. Simple. Okay. And this is second iteration. Okay, and third and fourth, I want you to do that. Question. So homework assignment is straightforward, right? I'm going to post the details of homework assignment. I'm thinking of first homework assignments is the completion of this. Number 2, I will give you not the number, but for example, mercy. Oh, mercy is too long, right? Maybe 3 characters, so that you can do it manually also. Third, implementation. Too much, right?
Probably.
You get the project.
Yeah. Okay, no implementation. I'll make it simple. Trust me. this time.
Clear symbols are complex.
Make it even more simple.
Yeah, even more simple. Okay.
Yeah.
Okay. So next module, which is excited. We don't need this anymore. Close. Okay. Cell network, wireless cell network. So we have cell signals. So look at your cell phone and find out where the cell signals comes out. Outline cellular architecture. Not in this order, okay? So this is, I'm going to, well, I'll keep updates. So, cellular network. Base station transmit to and receive from mobile at the assigned spectrum. Multiple base stations use the same spectrum. Service area of each base station is called cell. So now we know cell tower. This is a cell. This is cell. Each cell there is a cell tower, like access points of your Wi-Fi. Each mobile terminal is typically served by the closest base station. If you have your cell phone here, then the closest base station is this base, this cell tower. So communicate with that. If you move from here to another place, so that your cell phone and also the base station knows the capabilities of transmission and receptance of the signals, and then if one base station cannot reach your cell phone, then that base station will hand off. Meanwhile, if there is another base station actively, clearly access to your cell phone, then that base station will take over from that point. So the territory of each cell tower's base station needs to be overlapped, right? It should be overlapped. And frequency that our cell phone uses is usually 700 megahertz, 800, 900 gigahertz, and 1 gig, 2 gig, all the way up to from 700 meg to 2 gigahertz along that range. So the signal can reach your mobile device. That is the characteristics of that hundreds of megabytes and gigabytes frequency. If it is a kilobytes, then and if there is some obstacles, kilobytes is okay, right? But a little lower than that, then a lot of difficulties. But the frequency band that we are using right now is in that range. So usually we do not have any problem, not severe problem, although we are inside the building, like this time. We are inside the building, still we can receive cell signal. I do not know where the cell tower is available here, cell antenna. Anybody knows the cell antenna installed near here? Maybe?
The one that's near here?
Yeah.
Children's Village, right over there.
Which one?
Children's Village, right over there.
Children's Village? Where is the Children's
Just
Village?
like less than half a mile away.
Oh, that
Yeah.
far.
It's just a really
So
small.
not on our campus.
No. No, we have a repeater for police and fire, but nothing for cell phones here.
Okay. But we have a lot of students.
Yeah, they
Still,
did, but
still.
They said they were going to, and then they didn't because they don't care about us.
It's like sequence sucks.
Yeah. If you're in the new norm, you can't make phone calls. The RAs had to get a new phone so that they could use Wi-Fi and make phone calls. If there was an emergency, they'd hang out the window to make a phone call to 911.
It's not good.
No.
So they put a booster up on the roof for police and fire so that when they're in the building, they can actually talk to each other. But they didn't do anything for cell signal.
Okay.
That was because of home detention. We're working on it.
Good. I thought we have one inside the campus.
Yeah, we're supposed to. Yeah, no,
But I've never had any problem. I think when I am here, do we have another cell tower somewhere in Irvington? One from Dobbsbury. I think that's crowded because almost all the students are Main Hall or Victory, Mercy Hall. So you might have that problem. But when I am here, I've never had that difficulties. But anyway, might have another cell tower somewhere.
Less than half mile is still a good range.
Yeah. That's a really
But
small
number of users.
Yeah, that's a really small one. For like popular areas, they put one with like Old Green, but they didn't put one in Green because the city hates us. So
For example, if we have at certain points in time, if we have 5,000 students on campus, probably.
Sweet.
I mean, many times. How often do you check your cell phone? Right? I think at least once every hour, right? But Eureka, he keep playing with his cell phone.
Must be one in every town.
One in Terrytown?
we have 33
I see.
towers within 4 miles of us.
Yeah, Terrytown definitely have one.
Yeah, they have like 10.
What, 10
Yeah,
in
like
Terrytown?
10.
Oh, different carriers.
Yeah, for all the different providers.
Okay. All right. So, this is a theoretic presentation of the cell. Theoretic presentation of a cell. So, we have a cell tower. Cell tower covers, for example, these are the channels. Think about the channels. Okay, so to this direction, channel 2, to that direction, channel 9, channel 16, and 14, 7, 21, and so on and so forth. So at least channel is a subdivided frequency bandwidth. And through one cell tower, there is a wide frequency bandwidth can be carried. So based on this tower, let's say if we have an antenna here, then this guy receives the specific frequency band, which is not the same as the other angle where there is another antenna. It receives another frequency band, and from this angle another frequency band. So there is no intervention or interference between or among themselves. So it should be designed very clearly so that a specific frequency band needs to be open for user to use, and certain direction, certain area. Okay, so cell tower. This guy is a cell, right? Cell tower, cell antenna. They are not all, right? But this kinds of cell antenna. The territory from this cell antenna is not really proper circle, right? It's not, because depending upon the elevation geographically and depending upon the obstacles, it's not really ideally a circle. So all varies. So it is not really unrealistic to represent the cell tower coverage in hexagonal. Okay, hexagonal. So we have a hexagonal. The beauty of a hexagonal is that if we have this hexagonal, then this whole thing as a cluster, that is also hexagonal. See, here we have one hexagonal in the center. That's hexagonal, right? A cluster of that is also hexagonal. And it can grow further and further and further, like we have here. So we can characterize the frequency reuse, which means we have multiple cells. So cluster is a group of cells. So let's say it's not really a group of cells. Group the group of cells that they use the frequency bands. So which what it means is that here, if we have a cluster size 4, then we have 4 frequencies to be used with no interference. With no interference means not any two adjacent cells are using the same frequency. So if I am in one cell and there are 6 adjacent cells available, because we have a hexagonal, and none of those 6 having the same as mine. So all adjacent, any two adjacent, it doesn't matter, any adjacent cells should not have the same frequency band. Look at this. If you look at this, then if you have 4 frequencies, Then center we have 1, right? And then up we have 2. And then in the middle there we should have 3, so that they are all unique. And then the very next we should have 4. Therefore, any adjacent one have the same. Any adjacent cells do not have the same frequency band. So, if we have the same number, then it means the same frequency. So, in this case, number 2 here and number 2 here, they are the same, but all are different. See here, there is a number 2, and there is a number 2. They are all different. If you have a cluster size 7, then we use 7 different frequencies. They are all assigned with no duplication to the adjacent cells. So if you read the cells very carefully, then there is no any adjacent. There is no the same frequencies assigned. Okay. So that we can characterize the frequencies. Uppercase D is the minimum distance between the centers of cells that use the same band of frequencies. Because we call that co-channels. So, in certain situation, for example, I have here same frequency, and here another frequency. Then this is a minimum distance. I would say that is uppercase D. And uppercase R means radius of cell. Radius of cells. So each cell has a radius. There is a big R. And small d, there's a distance between centers of adjacent cells. So this is that. Okay. We have 2 adjacent cells. I made a small d. And then we have d equals r times root 3. Why root 3? We can compute it. We can prove it. Yeah, square root 3. I said explain why. And uppercase N means the number of cells in repetitious patterns, which is cluster. There is nothing but this. How many frequencies will be repeatedly used, but should not be assigned to any 2 adjacent clusters. So how many reuse factors? That is the capital uppercase here. Hexagonal cell patterns, the following values n possible. So n can be computed: I square plus j square plus I times j. J can be any number from 0 to any number. So if you enter any small combinations of I and j, the smaller one is 1. What it means is that if you have one cell, that there's only one cell, there's no adjacent, therefore you simply use one frequency band. That's fine, right? In theory. 3, that is also fine. If you have any adjacent, say here, if you have any adjacent, then I have here 1, 2, 3, 2, 3, 2, 3, then they're all different, right? Any adjacent that do not have the same frequency band. So that is also possible. How can you get number 3 here? If I equals 0 and j equals 1, then that will be number 3, right? So 0 square, 1 square, oh no. In what case would that we will have? Oh yeah, 1, 1, 1. I equals 1 and j equals 1, then 1 square plus 1 square plus 1 times 1, then that is number 3, right? So number 4 comes from I equals 0 and j equals 2. Then 2 to the power 2, there is 4, j is 0, there is 0, and another j is 0, this is all 0, so number 4. So these are the possible numbers that we can have hexagonal based cell configuration. Okay? So by using that number, then you can say, for example, oh, I want to use 19 channels of frequency from this cell tower, or 13 channels, 12 channels, things like that. And from there we can, having this, that also we can explain next week. Having that, I can explain that. We can solve this kind of problem. Look at this. We'll solve this problem next week. What would be the minimum distance between the centers of two cells with the same band of frequency if cell radius is 1 kilometer and the width of the factor is 12, which means 12 channels will be provided. Then what is the minimum cells? So that we need to set up the cell tower every 6 kilometers. That's what it is. Okay? If this is the answer. See here, this is the answer, which means every 6 kilometers we need to have at least one cell tower. So according to that, Chris, theoretically, you can prove that how many miles down and how many miles north or west, and find out this. Definitely we need to have Mercy College, another cell tower, and things like that. Okay. All right. So I'll see you next week. Okay. We'll stop here today.